Okay, so in this last video about astrophysics, we're going to talk more about the Big Bang model um, of the universe. Okay, and so the first thing we're going to talk about before we get to the Big Bang theory is we are going to go back to stellar spectra. And so one of the things we talked about earlier in this unit was all the information that we can find looking at the light coming from a star, right? And so we can tell, information about the chemical composition from stellar spectra, because emission and absorption lines, and each element has, like a unique fingerprint with the lines. And we talked about Wien's displacement law, how we can use the light coming off to kind of estimate the temperature of the star. But we can also use the spectra from a star to determine information about the velocity of a star or even an entire galaxy. And the reason we can do that goes back to something called the Doppler effect. Okay, and so the Doppler effect the Doppler effect is a wave behavior, just like refraction or reflection or interference or whatever. It's a wave behavior that applies to any type of wave. And basically, the Doppler effect, the definition of the Doppler effect is it's the apparent change in the frequency of a wave based on the relative motion between the source of the wave and an observer. Okay, and again, this is a wave behavior that applies to any type of wave, whether it's a sound wave, water wave, light wave, right? Any electromagnetic wave can experience the Doppler effect. Now, basically, in simple terms, what the Doppler effect means is that when something that is emitting a wave is moving relative to an observer, either towards or away from the observer, the frequency of the wave appears to the observer, it appears to change. And everyone has actually experienced this, although you might not have known it was called the Doppler effect. I'm going to put some quick links in to some short video clips just so you can see what I'm talking about. But typically you experience the Doppler effect when you hear like a siren in an ambulance or police car driving past. When it's coming towards you, the pitch of the siren sounds higher, and as it drives away from you, the pitch sounds lower. And the reason for that is that as it drives towards you, the sound waves get bunched together, and the wavelength gets shorter because the waves are kind of bunch up. And when it's going away from you, the waves kind of spread out. And so that's basically the Doppler effect. In essence. And so on the right here, you can see a picture of what this might look like for sound waves. You can see how when the ambulance is driving to the right towards somebody, the wavelengths get bunched up, and because the wavelength gets shorter, the frequency gets higher, and so the pitch of the sound gets higher. Whereas if you stand behind the ambulance, the opposite happens. Okay, that's essentially the Doppler effect. Now, everyone has experienced that with sound waves, whether you knew what it was called or not, but you might not have known that the Doppler effect also applies to electromagnetic waves, including light, meaning that if a source of light is moving towards an observer, the wavelength gets shorter, and if it's moving away from an observer, the wavelength gets longer. Okay, just like it is with sound. Okay, the difference is that, of course, light has color, and because blue light has a shorter wavelength, that's about 400 nanometers, and red light has a longer wavelength at about 700 nanometers. When it gets shorter, when it's coming towards somebody, we refer to that as blue shift, and if an object was emitting light moving away from us, we would call that red shift, which basically means that the light given off by the object would look redder than normal. And if it's coming towards us, it would look bluer than normal. And so if an object is emitting a light or any electromagnetic wave, then we can measure that amount of shift and use that to determine the velocity of that object. And it sounds kind of like magical, but this is actually used all the time. If you've ever seen like a speed trap with a cop car, they use those radar guns to measure how fast you're going. The way that they measure how fast your car is moving is through the Doppler effect, right? Because basically what happens is the gun they use like shoots a microwave beam, and it bounces off your car, goes back into the gun, and the gun can kind of detect what was the change in frequency from when the microwave was emitted to when it rebounded, and it can use that slight difference to determine how fast you're moving. And the technology is also used in things like Doppler radar to measure how fast storms are moving. Okay, now when you're talking about stars, Basically, when you look at the light from a star, we talked about like atomic spectra before. We see these lines when we look at the light through a star from a star through a spectrometer. And if the line, and we know exactly where each line is because we know, like we've talked about before, it's like a chemical fingerprint. Each element has its own set of lines, and we know exactly where those lines are. And so we can see if they are, if every single line is shifted to the left, then we call that blue shift. And if every single line is shifted to the right, we call that red shift. And we can look at the amount of shift and measure it to determine, number one, is that star moving towards us or away from us? And number two, how fast is it moving based off of the amount of the red shift or blue shift? Okay, and so again, we've talked about this before, but it really is amazing how much information we can determine from stars and galaxies just looking at the light coming off of it. Okay, and so again, here you can see the difference in the lines between red shift and blue shift versus being at rest, like in the laboratory. Okay, so stars that are moving away from us or galaxies that are moving away from us, we would expect to see more redshift. Actually, let's back up. Let's say we weren't expecting anything. It just so happens, experimentally was determined in the late 1800s and early 1900s that if you look at the spectra of a lot of galaxies and a lot of different stars, it turns out that most of them are in fact redshifted. And maybe we didn't know that before, but that is an experimental fact that most galaxies are redshifted. Okay, so I'm just going to kind of go through the notes here. Um, and so if you think about the implications of what that means, here in the notes it says Edwin Hubble, that's the Hubble telescope guy, um, and this other guy basically, like I said, looked at the spectra of lots of different galaxies and noticed that most galaxies show a redshift, which means that as we look at all around us throughout the universe, most galaxies and most stars are moving away from the Earth. Okay, meaning that galaxies are moving apart from each other. And so the implication of that is if you rewind that back in time, if galaxies are moving away from each other, then at some point in the past, everything had to be much closer together. In other words, if you go back far enough in time, all of the matter in the universe was concentrated at one single point, and then it just started like expanding. Okay, and that's kind of the one of the bases behind the Big Bang theory. Okay, and so the Big Bang model of the universe is a broadly accepted theory for the origin and evolution of our universe. And basically what it says is that somewhere between 12 to 14 billion years ago, the portion of the visible universe was very, very small, very dense, and very, 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 very hot. And since then, it has basically expanded. And as it has expanded, it has cooled into the universe that we currently are able to see. Okay, that's essentially what the Big Bang model is. We normally would go into more depth, but that's basically what it is. Okay, and we already talked about one key piece of evidence in support of that, which is the redshift of stars and galaxies relative to us, because again, that means that somewhere back in time, everything had to be much closer together. Okay, now there are other pieces of evidence that we'll just really briefly talk about related to the Big Bang theory. Remember that you can't prove anything correct in science. You can only, come up with pieces of evidence to support your scientific theory. But there are, pretty big pieces of evidence that support the Big Bang theory. Okay, so we already talked about the expansion of the universe. If the universe is expanding, which we know it is because of all the redshift we see, that would imply that at one point it was smaller, and at one point had to start expanding. And if it was smaller and everything was closer together, that means the temperature would have been higher, um, and it would have been more dense because all that mass would have been kind of grouped together closer. Two other pieces of evidence that we'll talk about real quick have to do with what's called cosmic microwave background radiation. We'll talk about that in a minute, and helium abundance. Okay, it turns out that, and I don't know how they do these calculations, but it turns out another piece of evidence for the Big Bang theory is that because helium is produced in stars, but there's more helium in the universe than we would expect there to be. In fact, about 23% of the mass of the universe is helium, and which is more helium than should be there if it was just produced by stars alone. And so, however, if everything was really hot, close to the beginning of the universe, then that extra heat would be able to cause fusion of helium, and that would explain kind of why we see as much helium as we do today. Okay, and so expansion of the universe, we talked about that having to do with redshift. Helium abundance, we kind of talked about that. The last thing we're going to talk about just really quickly has to do with what's called cosmic microwave background radiation. And we will just go through this really quickly, and then I've got a short video I want you to see. Okay, so basically in the 60s, these two physicists kind of made a mathematical prediction that if the universe was really, really hot and dense at the beginning, then there should be a lot of electromagnetic radiation left over from all of that heat. Okay, what's happened as the universe has expanded, it has cooled because that's how things work. It's like basic chemistry or physics. As things expand, they cool, which means that that electromagnetic radiation has also kind of cooled, and the wavelength of it has increased. And so what used to be like a lot of like heat and light is now actually stretched out into the microwave part of the spectrum. And these guys basically, did calculations and predicted that, in terms of like Wien's displacement law, the peak wavelength that would correspond to that would be somewhere in the microwave region and correspond to a temperature of about 3 Kelvin, which coincidentally is about the temperature of space. Okay, and so I've got a video clip I want you to see that kind of goes into more detail about the history of all of this. But it turns out that some other guys basically in the 60s detected the signal, um, which was good because that's kind of how science works, is you come up with a scientific theory and you make a prediction. And these guys, um, Dickey and Peebles, basically, um, you know, made a prediction based off of the Big Bang theory that, hey, this black body radiation, this microwave background radiation, it should exist. And then, lo and behold, these other guys find it with their giant like satellite antenna. And so the fact that they were able to make a prediction that was then, verified by experiment, that's a good piece of supporting evidence for the Big Bang theory. Okay, and so the very last thing I want you to do is I want you to watch a short video clip and then answer some questions related to that video clip having to do with that cosmic microwave background radiation, which this slide kind of describes as the afterglow of the Big Bang as the universe has expanded. Okay, so the three pieces of evidence having to do with the Big Bang theory, expansion of the universe because of redshifted light from galaxies and stars, helium abundance, and then the cosmic microwave background radiation. Okay, so I'm going to link this video in and then ask you some questions about that. Okay, so this is the last video of the unit, and that means that this is also the last video of the school year and the semester. It has been fun having you in IB physics for the past 2 years, even though this year's been kind of strange. I've enjoyed having all of you in my class. I wish all of you luck moving forward as you go off to do, exciting things with your life after high school. And yeah, drop me a line if you have any questions or need any help or anything. It's been fun, guys. Have a great day and good luck.